Okay, going live. All right. So we're going over like the last two questions on the problem set. So here's the idea. You can try this out next time you're in your car if you want, or if you're on like a train. So if you have a pendulum, well, you have to be like a passenger. Yes, don't do it while you're driving. Then if you're doing it while you're driving, how will you TikTok and drink your pumpkin spice latte? Because that's your two hands, right?
Pumpkin spice latte in mouth.
Yeah, you can TikTok with your knee maybe, and then do the pendulum with your hand, drink your pumpkin spice latte, and then drive with the other knee. There you go. All four limbs used. Okay. So what's going to happen if I start accelerating? This will happen very briefly, so you got to like kind of watch carefully. If I accelerate, you see the tilt? So I'll do it again with just my arm. So if this is accelerating, this system here, then for a moment the pendulum is tilted. Okay, that's what happens. So, but notice once I'll try to do this. There's no way I can get this captured on the film here. But if I start accelerating, and then once I hit that like normal speed, once I hit that constant speed, it's like what they call an inertial reference frame. So this one's really easy to test. If you're in your car on the highway or the interstate or whatever, and you just hold the pendulum, even if you're moving forward at 60 miles per hour, it's just going to be chilling there because the whole system is moving at that speed. And so it's in that moving reference frame. But if you slow down or sped up, if I'm driving this way and I hit the brakes, it would do that. Okay. So anyway, how do you analyze that in like a precise way? So this question says, here's the pendulum. There's the theta. Okay, so what kind of numbers do they give us for this question? 30 centimeters long?
40 centimeters long.
Okay, so the string is 40 centimeters long, so 0.40 meters. How big is the angle?
24.
24 degrees.
And it weighs 3 kilograms.
3 kilograms. Okay, great. So let's draw the force diagram. On this guy, there are, how many forces acting on this ball?
3. It's 2.
There's gravity and there's tension. Now, of course, the tension, we're going to resolve that into two vectors. So in a way, it'll be kind of like 3. There's going to be a down, an up, and a right. But if to answer the question, how many forces are there? There's actually just 2. There's tension and there's gravity. So let's draw the gravity. That'll be an easy calculation. 3 times 9.8, so 29.4 newtons. Great. This right here, I don't know that vector. Just kind of a little hint. I don't think the length of the string is going to matter a whole lot, but there's going to be this tension vector. So this vector here, try to draw this kind of thick, visible. Okay, there it is. But that vector has a vertical component. Draw my little box here. And it also has a horizontal component. Do that a little bit too long. Okay, everyone understand that? How it's got a vertical and a horizontal component? Okay. For $1 million. What is one thing we know about one of these components here?
They have to be to add up to the force of this tension of the string.
That's true. This vector plus this vector. Now, it's not true that the length of this vector plus the length of this vector equals the length of this vector. That would be Pythagorean theorem. But it is true that, yes, generally, a horizontal vector plus a vertical vector gives you a vector. That's true. But something simpler. Anyone else have an idea of, I actually know the value of one of these. Or I'll ask you this. What direction is the net force? Don't even look at the picture. Think about the problem. We're in a car. Does it say car? Okay, we're in a car. Accelerating, right? What direction is the acceleration? That way. So what direction is the net force? That way. So what's the net force in the vertical direction? 0. Okay, is the ball going up or down at all? No. So how big is this vector? 29.4. So, okay, let's make sure no one's lost in the digital dust there. This is obviously the critical step in the problem. We didn't really calculate that number. We more like just kind of reasoned it out based on a physics argument, right? So we understand why the vertical component of this tension vector has to be equal to the gravity vector. Or they have to be the same size. Did you lose your problem set, Colin? You did not lose it? Why don't you just take it out? We're doing well, we're doing the problem, so it might be a good idea to do it with us. Okay, so look at this triangle then. So this triangle, redrawing it is often a nice sight. No Trenton, sadly. Okay. So I'm redrawing this triangle over here. This is 24. This is the tension. This is, did I say that wrong? I'm going to say this is 24 degrees. This is 29.4 newtons. Okay, so how will I figure out? I have two options. I can figure out the tension. I can figure out the net force, right? So I don't know, we could do both. Does it ask us what's the tension? Yeah. Okay, let's just get both of them. How can I use these three? How can I relate these three things? Keep it simple, guys. SOHCAHTOA. Yes, the cosine of 24 would be adjacent over hypotenuse. Like that. So if you solve for tension, is everyone okay with the algebra step of going from here to here? Are we all okay with that? I could have also maybe written this like t cosine of 24 equals 29.4. In any case, okay, as long as there's no questions on this is what you end up with. Okay, we're cool with that. So,
You did two divisions. Well, multiplied it up and divided it.
Yeah, exactly. Multiplied it up, then divided the cosine 24. So I take 29.4 divided by the cosine of 24. And you get 32.2. And now, kind of like yesterday, what do you notice about that number?
It's bigger than the gravitation.
It is bigger than 29.4. It has to be. Otherwise, if this vector wasn't bigger than 29.4, then his vertical component couldn't be equal to 29.4. It wouldn't work out. Okay? So now, what do you think? Let's use blue here. What do you think I'm going to label this vector here? I guess there's more than one option, but it's very significant, this length here. Why is that very significant for the problem?
Displacement.
Kinda. You have the right idea, I think. It's the net force. Because remember, there's two vectors, there's two forces. This guy's vertical component gets canceled out by this vector. So what's left over, the net force, is just that. Okay? Or I might call it the tension in the x direction. But as long as you understand that the tension in the x direction, that is the net force. That's the net force. We all okay with why that vector there, the horizontal, is the net force? Okay. So Let's do that. I guess TX looks kind of nice. Okay, so now you have a few options. You can go, well, I don't know, sine of 24 is equal to TX over the hypotenuse. And the hypotenuse we just found is 32.2. That's one way to do it. I could have also, what if I wanted to use these two? What trig function is that? Tangent. I could have said, so alternatively, I could have said tangent of 24 equals TX over 29.4. And by the way, those are vanilla ice. It's the same. It's the same. It's the same answer. Okay. So that horizontal component of the tension would be 32.2 times the sine of 24, 13.1. How close are we to being finished with this question?
Very close.
Extremely, extremely, extremely close, because the last thing the question is asking us to do is to find the acceleration. Well, like we said before, this is the net force. This vector here is the net force. So if I write my famous F net equals ma, and the net force is 13.1, what was the mass? 3. I can get the acceleration. So it turns out 4.37-ish. Okay, so then in hindsight you go, well, it turns out that the car must have been accelerating at that rate, which is the same as saying the ball is accelerating at that rate, right? So again, two vectors, there's two forces, there's gravity, there's tension. You split the tension up into vertical and horizontal, and you say the vertical has to be the same size as the gravity. Then you do a little bit of trig to figure out what the hypotenuse is to get the tension. Another little bit of trig to figure out what the horizontal component is. And then you have to reason out that the horizontal component is the net force, and then you can find the acceleration. Is that a okay recap?
Yes.
Okay. Cool beans. Is that it for questions? Are there more questions to cover, to look at? True. Give it a shot. We can, in 10 minutes, we can look at it together if you get stuck, okay? End the stream. Millions of viewers.